Okay, hi. So a lot of students ask me to prove a certain problem for them because when we cover it in lecture, it's a little bit confusing at first. And I figured, hey, why not just create a short video that will do the proof so that way I can just reference it in the future if needed. So yeah, this is a complex, hard problem. I do not blame you if you didn't understand it the first time you came across it. I've had to really sit with it to completely understand it fully. So it is going to be a challenge to just try to explain it the best that I can. So let's take a look at the problem that we'll be looking at today. Okay, so the problem that we're looking at is prove that in any sequence of n squared plus 1 distinct real numbers, there exists a subsequence of length n plus 1 that is either strictly increasing or strictly decreasing. This fact that there is always an n plus 1 subsequence that's either strictly or increasing or decreasing, the fact is, or theorem, is called the Erdos-Szekeres Theorem. These were the mathematicians who I guess developed it. Erdos, very well known in the world of math. Szekeres, maybe a little less well known, but still. Just the fact that we tie these mathematicians' names to a theorem that we're about to prove should explain to you the gravitas of this, this problem and why it may be complex to understand. So yeah, let's take a look at it. So before we get into proving it, let's just make sure we understand what this actually means. So for the sake of an example, let's let n equal 3. So then we need to show that in a sequence of length 3 squared plus 1, which is equal to 10, in any sequence of length 10, there exists an increasing or decreasing subsequence of length n plus 1, which in this case is 4. So I'm just going to write down 10 real numbers and we'll take a look at it. So I've written down 10 real numbers and I'm looking for a subsequence that is either strictly increasing or strictly decreasing. So if I look at -5, I can actually find a strictly increasing subsequence by taking -5, 0, 1, 6, 7, 17, right, if I just rewrite it. So I have a strictly increasing subsequence, in this case of length 6, which also implies that I have one of length 4, because I can just ignore 2 of these values and get it. So in this example, it worked, and in fact, it will always work, either increasing or decreasing. Let's see an example where it is decreasing. So here we have another subsequence, and in this case, I can do 17, 6, 3, -1, -2, and that's a decreasing subsequence of length 4 or 5 in this case, which is perfectly fine. And sometimes, we'll have both of them, but the point is that we always have an increasing or decreasing subsequence of that length. And the key point is that a subsequence is just we're taking values out of the sequence, but we're considering them in the order that they appear. Cool, so I think now we understand what the problem is asking. Let's try to prove it. Okay, so we've sort of written down this arbitrary sequence of length n squared plus 1, and we want to show that it either has a strictly increasing or strictly decreasing subsequence of, whatever length. So we can sort of do some pseudo casework here. I say pseudo casework because you'll realize that it's kind of silly what I'm about to do. Okay, so for the sake of writing, I'm just going to call my sequence S, and now I'll sort of write out my pseudo casework. So this is why I was kind of saying that the casework is going to be a little bit silly. I'm going to case on whether or not S has an increasing subsequence of length n plus 1. If it does, then I'm done. I've found such a subsequence that we were looking for. If it doesn't, that's where the work is actually going to come into play. So we'll just sort of ignore case 1, because if our sequence falls into this situation, we're done. We don't have to worry about anything. Now we have to see, okay, it does not have an increasing subsequence of length n plus 1. If this is true, there are a couple of things we should keep in mind. First of all, we should keep in mind that we would need to prove that S has a decreasing subsequence of length n plus 1. Because to show that one of these is present, and we've already ruled one of them out, it must be the case that the other one is present. So that's what we're going to end up showing, that with this fact we can say that there will be a decreasing subsequence of length n plus 1. The other fact that we should keep in mind is that no matter what increasing subsequence of S that we look at, the length of it will always be less than or equal to n. And that follows from the fact that there isn't anything of length n plus 1. If we had something larger than n plus 1, that would mean we would have also a subsequence of length n plus 1, because we could ignore some terms, like I mentioned earlier. But with this, we know that every single subsequence will be, increasing subsequence will be of length at most n. Okay, so just writing that fact there. Up to this point, hopefully everything has sort of made sense and followed like some sort of natural thinking. This next step is something that I've spent the past couple of minutes thinking about, of like how to explain how to think about this. But if I'm being completely honest, I literally can't. It's just one of those things that like Erdos-Szekeres must have just been too big brain and they just like came up with it, and it's just like, I don't know an intuitive way of explaining to you why we're doing what we're about to do. That being said, we're still going to do it and show that it all works out. So, yeah. So, what we're going to do is for each term, we're going to consider the longest increasing subsequence starting from that term. So sort of ignore everything that comes before it, but starting from that term, what is my longest increasing subsequence? So we'll just give them variable values because we don't know what they are. So I'll call this like M1, M2, M3, like this. And this is not particularly helpful, but we do know from this fact from before that 1 is less than or equal to mi, which is less than or equal to n. Right? Or alternatively, I can say that m1 comes from the set 1 up to n. And m2 comes from the set 1 up to n. And so on and so forth. So while these are variables at the current point in time, we have n squared plus 1 of these variables, and we have n possible values that those variables could be. Are you seeing where this is going? Maybe. Let me sort of write it out. Okay, bear with my handwriting, but let's just discuss what I wrote. We had n squared plus 1 variables, each could take on n possible values. If we let the n squared plus 1 variable values denoting the lengths of these longest increasing subsequences, if we let those be pigeons, and the n length values be holes, then using the pigeonhole principle, we can conclude that there exists at least the ceiling of n squared plus 1 over n, which is equal to n plus 1 of these lengths with the same value. So this last little part is maybe a little bit confusing. So in other words, there are at least n plus 1 starting points, where a starting point is like a location in our sequence, such that the longest increasing subsequence from these starting points all have the same length. I can't really explain it in words much clearer than what I just did, but if this is still confusing, let's draw out a little bit of an example, and hopefully that should clear things up. Okay, so here we have a very carefully handcrafted sequence, and I will harp on the fact that it is very carefully handpicked, because remember, we are only considering sequences that don't have an increasing subsequence of length n plus 1. Remember, this is case 2. So this is a sequence of length 10, which means n equals 3. And if I did this correctly, which I may have not have done, this should have no increasing subsequences of length 4 or greater. And now I'm really paranoid that it does, but I don't think it does. So what we're going to do is basically simulate whatever I described over there. We're going to find the values of mi for each of these x values. So let's look at m1. We want the longest increasing subsequence starting from x1. So we need to include 4 in our subsequence. And then looking at what we could include afterwards, we could do 4, 18, 24. We could do 4, 16, 24, 4, 15, 20. It seems like the longest is 3. So we'll put a 3 there. Now to calculate m2, we want the longest increasing subsequence starting from x2. So we start with 18, and then we could do 1824 or 1820. So it seems like we can't do better than 2. Next, this one, 3, we could do 3, 16, 20. We could do 3, 15, 20. So it seems like this is 3. And then proceed to fill out the rest of these. And so we filled all of these out, and what all of this nonsense pigeonhole principle stuff that we just did, what that is saying is that if I were to look at these values of mi, at least n plus 1 of them must be the same. So in this case, at least 4 of them must be the same value. And sure enough, if we can see that the value 2 appears, in this case, 5 times. 4 or 5, you know, whatever, but at least 4 times. So this is saying I have found at least n plus 1 locations in my sequence such that the longest increasing subsequence starting from there has the same length. Now you're probably thinking, why in the world am I doing any of this? Well, maybe we have something here. We have at least n plus 1 values that all are kind of like together. They all share this similar property of having this like same length increasing subsequence. Why don't we take a look at the corresponding values in our sequence and see if we notice anything? So let's circle x2, x4, x6, x7, and x9. And if we look at these values, 18, 16, 15, 1, 0, that's a decreasing sequence. Could it be that these n plus 1 values that all share this same property give us a decreasing sequence? Because if that always happens, then we're done with our proof. We have found an n plus 1 length subsequence that is strictly decreasing. All that's left to do is prove that this fact does in fact always yield this decreasing subsequence. So that's what we'll do right now. So what we're doing is we have our original subsequence. Now we'll consider the xi's such that the mi's, their mi values, are all the same. the n plus 1 of those xi's that are the same, we'll consider those values, which will denote x sub k1, x sub k2, up to x sub k n plus 1. Again, we know we have at least n plus 1 of these by the PHP argument from before. And particularly, we're going to consider them in this sequence, such that k1 is less than k2, less than so on and so forth. Meaning we're going to maintain the order that they appeared in the original sequence, right? All of these indices are going to be like going from low to high. So yeah, we're going to argue, we're going to claim that xk1 is greater than xk2, which is all the way greater than xk n plus 1. If this is true, we have our decreasing subsequence and we're done. How are we going to prove this? We'll prove this by contradiction. We'll assume that this inequality relationship does not hold. If so, then we must have there must be somewhere in this inequality where there's not a greater than sign, but a less than sign, right? There could be multiple of those if, by contradiction this is not true, but there has to be at least one of them. And so we'll consider those two terms. And note that it is a less than and not a less than or equal to, because we're told that the sequence has distinct real values. So what do we know about xki and xki plus 1, besides the fact that one is less than the other? These both come from this sequence, this subsequence from above, xk1 through xkn plus 1. And what's the property of all of these x values? The property is that they all have the same length of the longest increasing subsequence starting from that position. So that means that that means something, but we'll worry about that in just a moment. Let us actually consider the longest increasing subsequence of one of these, starting from one of these terms. So let's consider the length of the longest increasing subsequence starting from x sub k I plus 1, this guy right here. And let's just say that that length is L. I mean, it could be called m sub k sub I plus 1, but that's just annoying to write out. We'll just say it's length L. What does this mean? If we were to consider the length of the longest increasing subsequence starting from x sub ki, then we have an issue. We know x sub ki appears before x sub ki plus 1 because of how we have this condition right here. However, if this is less than that, then we can form an increasing subsequence by considering an increasing subsequence starting from x sub ki plus 1, but instead, the first term, let that be x sub k sub I. What this means is that if the length of the longest increasing subsequence starting from this guy is L, the length of the longest increasing subsequence starting from this guy has to be at least L plus 1. Because we can use whatever sequence we had for this guy right here and prepend x sub k sub I. However, this is a contradiction. Why is it a contradiction? Because of the values that we're considering. We considered x sub k sub I and x sub k sub I plus 1 from this subsequence right here. But we obtained the subsequence by looking at the x sub i's whose mi's, which were the length of the longest increasing subsequence starting from that position, were the same. But here we have shown that if there was this less than relationship, then they must not have been the same value. Therefore, that's a contradiction. So this relationship holds. And what does that mean? this is our decreasing subsequence. And that's the end of the proof. Yeah, it was long and long-winded for certain, but it's good to understand what we did, right? We're just like, okay, suppose there is no increasing subsequence of that length. Let's show that there's a decreasing subsequence of that length. And yes, admittedly, that whole pigeonhole principle thing was kind of counterintuitive, but it gave us good information to work with. But I certainly hope you see what the contradiction is and how that yielded a decreasing subsequence. There aren't too many takeaways from this video. Just hopefully you understood the proof now. It's a tough problem for sure. I mean, students have been asking me about this for so many semesters, so it's about time that I just put something together. So hopefully this was helpful. Hopefully you learned a thing or two. And yeah, as always, take care.